Let's talk again about what the first and second derivatives of a function can tell us. Now I've given you a function here, f of x equals x to the fourth minus 3x cubed plus 10. Let's take the first derivative by moving the 4 down in front and subtracting 1 from the exponent. Then 3 times negative 3 is negative 9, subtracting 1 from the exponent, and of course the derivative of 10 is nothing. Now let's take the derivative of our first derivative, and that will give us our second derivative. 3 times 4 is 12, subtracting 1 from the exponent gives us a 2. 2 times negative 9 is negative 18, subtracting 1 from the exponent gives us 1, which is understood. Now remember, we're going to set our first derivative equal to 0. This will hopefully tell us any maximum or minimum points that we have, but it might also give us an inflection point. We're just going to explore and see what happens. So what I've done is I've taken the first derivative and set it equal to 0. I now factored out the common term of x squared from both terms, which left me with this product. At this point, I know that I have the product of two things that equals 0. Either the first thing has to equal 0, or the second thing has to equal 0. So, if x squared equals 0, that must mean that x equals 0. If 4x minus 9 equals 0, then that means that 4x equals 9, and dividing both sides by 4 gives us our final answer of x equals 2.25. Now these are both critical points. We're not sure exactly what's going on at those two critical points, but let's first of all find out what the corresponding values for y would be. In other words, where would these points actually lie on our curve? So going back to my original function, which up here was f of x equals x to the fourth minus 3x cubed plus 10, I will first plug in a 0 into that function. That gives me 0 to the fourth minus 3 times 0 to the third plus 10, which equals 10. The second point I need to plug in, or second value for x, was 2.25. Plugging that in gives me 2.25 to the fourth minus 3 times 2.25 to the third plus 10. This gives me a value of 1.46. Now, here's my graph. Here's my origin. So I will plot the point 0, 10 right here. 2 1/4 would be approximately right here, and then moving up about 1.46 would give me my next point right here. Now notice already I'm predicting that this is going to be a decreasing function between this point and this point. Between 0 and 2.25 I would anticipate a decreasing function. Let's return to our calculations now. And I've plotted on this number line a 0 and a 2.25. Again, those are my critical points, and I want to figure out what's happening in essence in the three regions that are going to be my graph now. I want to know what's happening to the left of 0, so I'm going to plug in a negative 1 to explore that option. I want to know what's happening in the middle. Even though I predict it's going to be decreasing, we're going to do the calculation to be sure. I'm looking for a point between 0 and 2.25. The easiest whole number to plug in is 1. And on the right side of 2.25, the easiest whole number to plug in is 3. Now let's do the calculations. The first derivative of I'm going to plug in negative 1 into my first derivative, which we remember is 4x cubed minus 9x squared. This will give me the equation or the slope of the tangent line at this point. Plugging in the negative 1 gives me 4 times negative 1 cubed minus 9 times negative 1 squared, which equals negative 13. So at this point on my graph, my function is decreasing. It's going down. Now let's plug in a 1 and see what's happening there. Plugging 1 into my first derivative gives me 4 times 1 cubed minus 9 times 1 squared, which gives me negative 5. Now what I have here is another place where it's decreasing. So where we might have been expecting this to be a minimum point, it actually appears at this point to be an inflection point, since the graph continues downward through this entire range. Had this been a minimum, instead of continuing down, it would have gone down, and when I got to 0, it would have started back up again. But since this is decreasing, this appears now to be an inflection point. Finally, let's determine what happens when x equals 3. Plugging 3 into my first derivative gives me 4 times 3 cubed minus 9 times 3 squared, which equals 27. So at this point, my graph is increasing again. So it decreases on the left, continues to decrease in the middle, and increases on the right. Let's do a sketch now. Returning to my graph, something like this is going on. It's decreasing down to there, then at 0, I start decreasing again, but suddenly it turns back up and comes up this way. Now, obviously, this is an inflection point. It would appear to me as well that somewhere in this area on the curve there will be an inflection point as well. If the curve is concave down here, and there is indeed an inflection point, concave up here, excuse me, and this is indeed an inflection point, then this part would be concave down, and this part concave up. Let's explore to see if there is indeed an inflection point at this point, and also confirm that this is indeed an inflection point. Alright, let's explore again what's happening with our function. First of all, again, I think we have a minimum here when x was 2.25 and our function value was 1.46. So those are the coordinates of what I expect to be a local minimum. I expect that the point 0, 10 is an inflection point, and I anticipate that there'll be another inflection somewhere in this area on the curve. So let's use the second derivative now to explore this. First of all, let's confirm that it was indeed a minimum point when x was 2.25. I will plug that into my second derivative, and if it is indeed a minimum, that means the curve is concave up, so the second derivative at that point should give me a positive value. When I plug 2.25 into the second derivative, and recall what our second derivative was again, when I plug in 2.25, I get 12 times the quantity 2.25 squared minus 18 times 2.25, which does indeed give me a positive value of 20.25. Now, let's see where our inflection points are. Remember, an inflection point is a point between where it's concave up and concave down. At that point, since it's neither concave up or concave down at that instant, our second derivative should actually be equal to 0. So, first thing I did was set the second derivative equal to 0 and factor out my common term of 6x, which left me, when I divide out 6x, 2x from the first term and a negative 3 from the second term. Well, now I have the product of two things which equals 0 again. Either x must equal 0 or 2x minus 3 must equal 0. Adding 3 to both sides gives me 2x equals 3. Dividing by 2 gives me my solution of 1.5. Continuing, what it appears to be happening here, again, is I have an inflection point at 0 where I expected there to be one, and I have another inflection point at 1.5. Let's find the value of the function when x equals 1.5. Plugging my 1.5 back into my original function gives me 1.5 to the fourth minus 3 times 1.5 cubed plus 10, which gave me a value of 4.94. If I come back to my original graph, that point appears to be approximately right here on my curve, which is where I anticipated it would be. Remember, we knew that this was concave up. I would therefore anticipate plugging in a value that this portion of the graph would be concave down. So let's plug in 1, which is to the left, and see if I do indeed get a second derivative which is negative.